Hey guys, we are in our last topic for chapter 5. You probably thought we'd never get here. This one's going to be over the Clausius inequality. If you all remember when we started chapter 5, we were talking about the second law of thermodynamics, and we had the Kelvin-Planck statement, and we said we were going to have the Clausius statement. That Clausius statement, if y'all, oops, I'm missing a U here. The Clausius statement was the one that stated that we can't transfer heat from a cooler body to a hotter body. So essentially, you're not going to be able to warm up a hotter body using a colder body. That just wouldn't work. And everybody knows that. Now, this inequality we're going to have, this is going to basically make use of this statement, and it's going to let us see if there are irreversibilities in our system. Remember, irreversibilities make our system less efficient. The inequality is going to be applicable to any cycle without regard to the body from which the cycle receives energy by heat transfer or to which the cycle rejects energy by heat transfer. So basically it doesn't matter which body you're using to get your energy to or from. It'll work for any case. Now let's go ahead and write down the actual inequality. And this is what it looks like. This is the integral symbol with the circle over it. And then we've got delta Q over T, and B equals negative sigma cycle. This is the actual equation. And a lot of students don't like the way that equation looks, but it's not going to be that bad, I promise you. So what this is telling us, this delta Q here, this is just basically representing the heat transfer at a part of the system boundary during part of the cycle. That's all this is. So it's delta Q because it's not the full value of Q. Then T, that just represents our temperature. B, this is just telling you you're going to evaluate this part right here, this equation, the delta Q over T, at the boundary of the system. And this integral here, this is a line integral, and this is just indicating that we're going to evaluate along the boundary for the entire cycle. This sigma term, the description that most books give is that it is kind of like the strength of the inequality. Okay, so using all of this, if you were to go through and do all the math, the equation that we're going to use that goes along with the inequality is that sigma cycle is going to be negative QH over TH minus QC over TC. So this is the one we are going to use. So not too bad, right? This one looks a lot better than this. So we'll use this one. And depending on the value we get for sigma cycle, we can figure out if our cycle has irreversibilities, if it doesn't have irreversibilities, or if the cycle is just impossible to have at all. So a few different choices. If that sigma is equal to 0, that means no irreversibilities are present. In the system. All right, and that would be the ideal case. That's what you would want. If it's greater than 0, then we do have irreversibilities. All right, so usually you'll have this because you're always going to have irreversibilities unless you're dealing with some theoretical case, typically. Now, sigma cycle, if it equals, actually not equals, if it's less than, let's put less than, if it's less than 0, then that means that cycle is just impossible. So there's no way you could operate that cycle. So these are the three things that we need to remember. These go with this equation here. Okay. So using this along with these three statements, we can figure out if we have irreversibilities or not, or if our system's even possible. Now let's go ahead and we'll go right into the example. So this will be our last example for chapter 5. And this example says that we have a system. It's undergoing a power cycle while receiving 1,000 kilojoules by heat transfer. The temperature is going to be 500 K. It's discharging energy by heat transfer at a temperature of 300 K. We need to determine sigma cycle if the thermal efficiency is 100%, 40%, or 25%. Now, first, before we get started, let's just draw a picture. Because y'all know I like to draw pictures, even though I'm not very good at it. TH is going to be 500 kelvins. Got our system. And down below here, we've got our cold reservoir, so this temperature is going to be the 300. Now, this is a power cycle, so we're going to have an energy transfer by heat from the hot reservoir to the system. So there's QH. And it told us that that was 1,000. And that's in kilojoules. So there's QH. Now remember the power cycle, we're going to have work going out. So let's draw that arrow. And then, since it's not 100% efficient, we're going to discharge energy to the cold reservoir. That's going to be QC. All right. So that's our setup here. That's what we got going on. We're going to use the Clausius inequality because we want to find this sigma value. Let's write the equation down. So remember, sigma for the cycle will be negative QH over TH minus QC over TC. Now, what we need to do is we're looking at the thermal efficiency. So remember, for our power cycle, that's eta, that fancy little N looking symbol. So we're going to have eta equals 1 minus QC over QH. That was the equation we developed before. Now, we have QH, we have TH, we have TC. We don't have QC. Let's use this equation here to find QC. Then we can have everything we need. Now QC is 1 minus the efficiency times QH. We were given the efficiency, right? We have 3 different values for it. We just need to plug those in here, and then that'll give us our QC. So then let's write our new sigma equation. So sigma cycle will be negative QH over TH minus 1 minus eta QH over TC. So this is what you get when you plug in QC right here. All right, so for part A, we're saying the efficiency is 100%. Now, after all the things we've talked about efficiency, we already know that that's not possible. We're not going to have 100% efficient power cycle. If you could do that, you would be a very wealthy individual. So let's say eta is equal to 1 here because it said 100%. Now we're going to use our values in this equation. So sigma is going to be negative 1,000 kilojoules per 500 Kelvin. And then we're going to subtract 1 minus 1. And then QH is 1,000 kilojoules. Put that over TC, which is 300 Kelvin. Now, if you look, this ends up going away, right? This is 0. So this whole second term we don't have to worry about. And your sigma here is negative 2 kilojoules per Kelvin. Now we're going to take this value and we're going to look up here. Just like we suspected, it's less than 0. That means this cycle is impossible. You're never going to be able to get that 100% efficiency. So we'll just put impossible right there. Okay. So there's that, and I guess you want to circle the actual value too. That was part A. Now let's see if 40%, let's see if that one's possible. See if we have irreversibilities, what we got. So now our efficiency is 0.4. So we're just going to plug everything into this equation again. So we get negative 1,000 kilojoules per 500 kilograms Kelvin. Then we subtract 1 minus 0.4 times 1,000 kilojoules. Put that over 300 Kelvin. All right. Now on this one, these two are going to end up being the same value. So you end up getting a 0 here. So sigma is going to be 0. Now if we get a 0, that means no irreversibilities. Let me write this down here, I'm out of room. So there's no irreversibilities, that means it's internally reversible. Okay, so if it's internally reversible, we're going to get that 40%. Now, last one. C, the efficiency was 25%, so that's 0.25. You guys know the routine. We're going to plug all the values into the sigma equation and then see what we get. So it'll be negative 1,000 kilojoules per 500 Kelvin. We want to subtract 1 minus 0.25 times 1,000 kilojoules over 300 Kelvin. And for this one, if you do the calculations, you get 0.5 kilojoules per Kelvin. That's what you'll get for sigma. This is greater than 0, so this means we have irreversibilities. Okay. And notice if you have irreversibilities, our efficiency is lower than it was when we said it was internally reversible. Right? Irreversibilities reduce your efficiency. But that's how you can use that Clausius inequality. It's simple and easy to use. Just gives you an idea about the performance of your system. So that's the end of chapter 5. Finally made it. One more chapter. So in the next chapter we will talk about entropy. I will see y'all there.